Okay, great. So first, what we did learn that if there is a variable, if there is a scalar, which we really want to measure across the space and time. So this is the most fundamental way of, deriving the variation of that scalar. And from there, what we obtain the definition of the substantial derivative. And what is this substantial derivative? This is nothing but an agglomeration of a set of partial derivatives, right? So in that we obtain a kind of local variation where we really look for the variation of the scalar with respect to time, and a part which is associated with the flow, that is the convective variation. And together we called it as a substantial derivative, which is dc by dt. This c can be mass, this c can be momentum, this c can be energy, right? So say suppose in the 6th or 7th standard, when you were first introduced with the principle of the mass balance, with the principle of the momentum balance, with the principle of the energy balance, if we really think about an engineering definition of that, this is the engineering definition of that, where we say that this c can be mass, this c can be momentum, this c can be energy, this c can be entropy, right? Now in that process, what we do, we obtain a kind of balance principle, and then when we involve x, y, z, and t, essentially we are bringing the aspects of the geometry. Say suppose there is earth, suppose there is a car, suppose there is sun, right? Suppose there is an aircraft, suppose there is a ship. So we can really see, like, all these objects, and around that, if we are really looking for the variation of this variable, we can really put up a kind of framework in the Newtonian mechanics in order to obtain the variation of that around that geometry. Now you know that since this is a differential equation, we require at different levels the initial conditions and at different levels the boundary conditions in order to solve this. Now moment I solve for C, if I get a functional form with the boundary conditions, and after enforcing the boundary conditions, then what happens? Then I know if this scalar is temperature, I know the temperature profile. I will come to know this is, suppose if the engine is running, then what will be the temperature inside the car, outside the car, on the surface, inside the engine. I can really know the entire process of the temperature, and then we may really design that whether it is heating up beyond a critical temperature, beyond a particular certain temperature, which is not suitable for the materials that are used in order to really house the engine, and then how to cool them down, this and that, and so on and so forth, right? So you see that, although we did learn in a very conceptual manner the mass balance, momentum balance, and energy balance, so the mathematical manifestation starts here, right? And that actually connects. And then we did all these, definitions of different part things, like what is ordinary differential, partial differential. So this is essentially, if you really want to be a very good engineer, this should be your first slide of understanding. You will be asking yourself this question, that do you understand this slide properly or not? First conceptually, and then mathematically, right? More your understanding improves as you progress in your life, career, whatever. So then what happens? Then your competence associated with your engineering skills goes up, and that's where it comes, like, now say suppose when I learned the conceptual part, how exactly I apply the usage of the substantial derivative or total derivative, or this is also called the Eulerian derivative, right? Now how exactly I apply this in terms of, like, manifesting the mass balance, momentum balance, and energy balance, right? So we took a scalar phi. We said that this capital phi is nothing but total amount of some property of the system, while small phi is the same property but per unit mass. So these are called the specific properties. If you are reading thermodynamics now, you will see that these are called the specific properties. Say suppose I am looking here enthalpy, this is specific enthalpy. If I am looking of entropy, this is specific entropy. If I am looking at internal energy, this is specific internal energy. Specific means, internal energy per unit mass. Okay. So, in that you will find that, say suppose this is a very, very arbitrary control volume. And what is the balance principle? So what is the change of any property in this system? Rate of increase of the property in the system. is equal to what? Rate of increase in the property of the control volume itself, which is a volumetric property, and rate of efflux of the property across the control volume boundary. So essentially, if you have a control volume, something can increase here, right, in the volumetric part itself. And what will happen? Something will come from this side, something will go from this side. So it's basically you are considering an open system inside. In that sort of situation, whatever is the change in the property here is the resultant of these two. Now, how do you mathematically express that? You mathematically express that. Say, suppose phi is my specific property. Rho dV gives me what? In a differential volume element, what is that property that is changing with respect to time? So del T of rho phi dV is what is that property that is changing with respect to time in that control volume. So the volumetric part is taken care of. This part is associated with this. Whereas whatever is coming in and going out, you are just, this particular things means, you are first, creating a differential area dA, and you are integrating over the entire surface to really note that how much has come in and how much has gone out. Right. So this is nothing but the rate of efflux of the property across the control volume boundary. So phi can be any property like mass, momentum, energy, entropy, enthalpy, internal energy, kinetic energy. And then, you can really come up with the differential. If somebody asks you, can you tell me, say, suppose if there is a car geometry, what is the variation in the kinetic energy? Kinetic energy being a scalar property, right? You can really enforce a Reynolds transport theorem there in order to really see what exactly is the change in the kinetic energy, right? This is true for any scale. Now, once we learned that, then we started testing this for the mass, and you saw that, once I say that capital phi is mass, that means small phi will be 1. And if I enforce that straight away, what I get the mass balance equation. And this you are studying in fluid mechanics. And then what I get the continuity equation for an incompressible flow, right? Then what we did, we started probing on, say, Newton said that rate of change of momentum is proportional to the force that you apply, right? So this is your second law of Newton's motion, that, force, whatever force you apply. Now, can somebody tell me why this concept of force is coming here? Why suddenly in mass and energy balance, the force came into picture? Anybody has any idea? Can anybody give me any clue? Why I am looking for a momentum conservation? Why is it so important? Say in scientific and technological domain, why, I need to really define a parameter called force, and then I need to really look for, I mean, of course, mass balance and energy balance would have been sufficient, right? Can anybody tell me what is first law of thermodynamics? Equational form. Do you remember? Anybody in the class? Anybody in the class remembers what is first law of thermodynamics?
Change in internal energy equal to work done plus heat.
Yes, very nice. So change in internal energy is equal to what? du is equal to du is equal to what? So what is your formula?
Du equal to Q plus W.
Right. du is equal to, dq plus dw, right? Now you tell me, this is your energy part, right?
Yes, sir.
This is your total energy, right? In that you have a part which is heat, correct? And that's why we are doing this course called heat transfer. Can anybody tell me what is this dw?
Work done on system.
How do you define it? What is the definition of work done on the system?
Integration of PdV.
PdV integration of, in terms of, like, very nice. P of dV integration of PdV is the definition coming from thermodynamic point of view. But what is the more fundamental definition of work. How do you define work?
Force times displacement.
Fantastic. How do I define in a vector? If force is a vector, displacement is also a vector, right?
Dot product.
So you take a dot product between force and displacement in order to, or it is written in general in terms of S, small s, right? You have a vector called S, you have a vector called force. Now force into displacement becomes your work done, right? Now question is that, what is this force? This is where the question came. See, when you say, suppose when you enforce mass balance, you immediately realize, say for an engineering system, if I go for only mass balance, that is not going to solve me the problem. This is not going to solve my problem. What do I know from this equation? What do I know? How do I know that how this see, there are three velocities here and there is only one equation, right? So it is not a self-sufficient equation, correct? More importantly, when you really look for the energy balance, one part has associated with what? As one part is associated with the heat, the variation of heat. This can be managed with internal energy, enthalpy, and there are many ways to manage. You have to really come up with a foundation how to manage this Q. That we are going to study today at the end of the class. That how exactly it happens for a conduction, how exactly it happens for a convection, radiation. Those things we are going to really study. But more important point is that I also have to really worry about dW, because this is where, any type of engineering system is more, prone towards looking at this aspect, because this is basically I'm trying to minimize my loss. A part of it I'm utilizing, a part of it is not available to me. But this part is totally available to me in order to really perform any engineering work. This is my the cash rich situation. In a business, if I have a lot of cash going in, so that is what is DW. Whereas here, I'm just in a break even and I'm trying to economize the system. In that, one of the major component is the force. Now question is that what is force? So when that question came, so people said that what is force? So force, while defining the force, people have performed n number of experiments, and from the n number of experiments, people have found out that there is a similitude between force and the rate of change of momentum. So force is proportional to the rate of change of momentum. Now, why momentum? You see that mass balance has some correlation with the velocity, whereas momentum is also some correlation with the velocity. Momentum means per unit mass. You will see you are exactly looking at the velocity, which has been proved in the mass balance equation. So essentially, say for a continuity equation, you are looking for the velocity profile. If you know the velocity profile, if you know the density, you are able to enforce the mass balance. Same here. So in the Reynolds transport theorem, what you do, you replace rho v, and if you replace rho v, you come up with the entire substantial derivative, which is rho into dv by dt into dv in control volume. This essentially means what? Mass into acceleration. This is acceleration. This is mass per unit volume multiplied by volume. That means this is mass into acceleration in the entire control volume. Now what you do, you equate that part with the total amount of body forces that are present and total amount of surface forces. So it's a volume integral body force like gravity, like centrifugal force, like electromagnetic forces, like van der Waals forces, like intermolecular interactions. Every level, you use this as a volumetric force, whereas for surface force like friction, like surface tension, all these things, if you just accumulate, you end up getting an equation of motion. What is this? This is force equal to force is proportional. This is the total force on the right hand side. This is force per unit volume, right? And this is mass into acceleration per unit volume. You take a volume integral of that, and then what you have the force balance across the space. So you see that first I have made ready the mass balance, then I have the definition for force, right? Now then I have to now really look for what is my energy balance, right? So in the same Reynolds transport theorem, My capital phi is here what? The capital phi is here what? What was my Reynolds transfer theorem here? What was my equation? The equation was this, right? So if I just come and really compare here, that what is my situation here? That this capital phi is nothing but I'm taking as my total energy E as capital phi, and small e is like capital E by M. So this is my specific energy. Rest you will see that I have replaced everything as per the Reynolds transfer theorem. Now what I say, what is my total energy? So total energy is my internal energy plus kinetic energy. You can add potential energy also, but for the time being, for the sake of simplicity, we can just ignore that part. Now, can anybody tell me, so if V is a velocity vector, how do I define kinetic energy?
Half mv.
If V is a velocity vector, how do I define kinetic energy? Half mv square when V is what?
Magnitude of it.
Magnitude of velocity, right? But if I am saying that if V is a velocity vector, how do I define kinetic energy? So you can see I have defined it here. Half into m into V dot V, right? And that is what is giving you the V square associated with the kinetic energy. Correct? So your total energy is your internal energy E, small e, and the kinetic energy M is gone because why? Because this we are taken as a per unit mass system. Right. Now, say suppose if you apply the Gauss's divergent theorem, so what happens? This remain volume integral, the surface integral is converted to volume integral. And then, if you take the dv out and if you keep them together, so you see that you straight away get what? You straight away get what is dE by dt? dE by dt is nothing but rho into, this is your energy. What is this called? Now, what should I call this?
Local energy.
What is that?
Local.
Yes, local what?
Yes, sir.
What is that? Local?
Power.
Local variation of energy, right? Yes. Local power, right? At any particular XYZ, how energy is varying. And what is this?
Convective.
This is the convective energy, right? So you can straight away see that there are two components associated with that. What are those two components? Now, one component is associated with what? One component is how the energy is changing with respect to time at a particular place. And second is that since I have taken an open system and I know that there will be some flow, say suppose the gasoline is coming, getting burned, generating heat, and then the hot gas is going out. So this is an open system. This is not a batch system. So I really have to consider the flow of the gasoline that is coming into the reactor and then the gases, the hot gases that are going out. So that is embedded into the system. Right? Now, this E has a catch. Please don't confuse with this, the E and this E. This, what I'm talking about is here, what I'm talking about is the total energy ET. Right? Now, in this total energy, you tell me there is this internal energy part and then there's a kinetic energy part, right? Now, this kinetic energy is associated with what? This kinetic energy is associated with, like, say suppose the work that you are doing, that the work that you are supposed to do, which has a very big correlation with what? Which has a very big correlation with the forces that you apply. Okay, and what are the two types of forces that you apply? F is the, here we already mentioned that this F is the body force. F is a vector, it's a body force vector, and T is a surface force, which is also a vector. This is force per unit area, and this is force per unit volume, because this is a surface force and this is a body force. This is something like pressure, stress, right? And this is something like gravity, which is force per unit volume. So straight away you see that when I really try to see what is my total change, substantial change, that means local and convective, I say that what I do, I take F dot V dV, T dot V ds. Now, what am I doing here? Can anybody tell me when I take F dot V, what is the parameter that I am getting? If I take a dot product of V with respect to F, what is the parameter that I am getting here?
Surface force.
Force. Force, if I take a dot product with respect to V, what is the parameter that I am getting?
The power.
Very good, excellent, right? So if I just take the time, see here you see that what we were discussing previously, what was we discussing, that here you require, I mean, of course, in engineering system, you can always expect that there will be a denominator dt. Now this will be dq by dt, and this will be dw by dt, right? So essentially, every engineering process is a time-bound process. So this will be rate of internal energy, the rate of heat loss, and this is the power associated with the system. And with power associated with the system, what you do? Force into S dot. S dot is nothing but now you are getting from displacement with S dot, you are getting the velocity. So when you multiply the velocity, essentially you are looking the variation of force with respect to time. That means what are you looking exactly at? You are looking exactly at the work done by the system, or work done on the system, work done by the surrounding on the system, or work done by the system on the surrounding. So essentially, the total energy that you are talking about, first is the total work done by the volumetric forces, total work done by the surface forces, and then what you do, you see that the internal energy is taken out by the heat flux vector. So what you do, you say that whatever is the internal energy, I'm just going to consider about the change in the internal energy. And internal energy change means I'm just going to consider from the surfaces how the heat fluxes are going out of the system. Because heat generated means you need a reaction that can also be included later. So the volumetric part of heat is like, say suppose if you have a reactive system, if you have mixed sodium with sodium hydroxide with hydrochloric acid, right? It is going to give you sodium hydroxide, sodium chloride, and water, right? Now that sort of reaction, if you are committing inside, then you should also have a Q dot V dV component, right? But for the time being, you just consider that there is no such reactive process, just to keep the entire system a little bit simpler. So we consider the total work done by the volumetric forces, total work done by the surface forces, total power generated by the volumetric forces, total power generated by the surface forces, and the heat loss associated with that. So essentially, you can see that I am getting into this is the most common definition, most general form of the first law of thermodynamics. Right? Now, these are two surface integrals. I convert them to volume integrals. And then if I just take all the volume integrals together, I get the pristine form of energy balance, where this is the rate of change of energy. What is this part? Can anybody tell me in the energy balance? Just now you have told. What is this part? Yes, quickly. Just now you have told here. What is this part? This is the coming
Local
from the
part.
Is it local or convective? This is the local part, right? The two components are coming from here, right? So you have 1, 2, 3, 4, 5 components, correct? Now you have taken them, all of them towards the left hand side. This one minus this plus this, right? So that's the way it is written, right? So this has two components. These two components written here. This is for the total energy. This is the local energy, local change of energy. This is the convective change of energy. As the fluid is flowing, what is the energy that is getting dissipated with respect to that? So this is the convective flow of energy. This is the work done by the volumetric forces. This is the work done by the surface forces. And this is the total volumetric heat flux. Sorry, heat flux associated with the system. Now this gives you the total energy balance equation, which appears like this is the differential form of the total energy balance equation. Now, in this energy balance equation, if you integrate over any volume, right? This has only one limitation. This particular equation has only one limitation. I did not consider any chemical reaction here. In that chemical reaction, if I add a chemical reaction, you just will have to add an RA term here. Other than that, everything is taken into account. You know, as many forces you have in terms of the volumetric forces, say suppose you have centrifugal force, suppose you have intermolecular forces, you just keep adding them here. If you have the surface forces like friction, these, that, you keep adding them here, right? This will be what you will see. This will be associated with number one, heat conduction. We are going to study today. This will be associated with heat convection, right? This will be associated with heat radiation. And then you just have to add another component here, which is RA, which is associated with the heat generation. That is the only term we are missing here. Other than that, this is the most comprehensive form of the energy balance associated with the total energy. Now, you can very simply see that, you know, if I really arrange them properly, so this is the local, this is the convective, this is the work done by the body forces, this is the work done by the surface forces, this is the total work done, rate of work done rather, because dt is always there at the bottom. Rate of work done by the fluid body and surface forces, and this is the rate of heat transfer to the fluid, positive for an outward transfer, right? So now you see that when you do mass balance, when you do momentum balance, you are in the domain of fluid mechanics. When you are doing energy balance of the system, this heat transfer subject is originating from the addition of this particular term, right? Now, our objective next onwards will be to really take care of this part, because this anyway you are taking part in fluid mechanics, right? This you are anyway taking part in fluid mechanics. So we are not going to focus on this. We are going to focus how this is changing with respect to this, right? Now, say suppose you want to look for, see, essentially total energy, we have said that internal energy plus kinetic energy, right? So you can really separate out the part associated with, see, this is the part associated with the internal energy, and this is the part associated with the kinetic energy. You can really separate these two out, right? So if you take the internal, why am I separating this out? Because internal energy will be mostly associated with my heat transfer, whereas kinetic energy will mostly associated with my work done. So work done, what is coming? These are surface and volumetric forces coming, whereas in heat transfer, what is coming? The parts that are associated with the heat generation that are coming together, right? So once that happens, you will see that your simplified heat transfer equation will come like this. Now, what you can do, you can write enthalpy is equal to internal. You know that this is by definition, enthalpy is what? Internal energy plus PV, right? So that can be written as P by rho. This is specific. This is specific enthalpy. This is specific internal energy, and this is 1 by rho is the specific volume, right? Density can also be talked about the specific volume, right? So 1 by rho is called the specific volume. So in that, if you replace this internal energy with enthalpy, so that gives you the most comprehensive form of what? The most comprehensive form of the energy balance equation, which is associated with only the heat transfer. Because you see that I have segregated out the kinetic energy here. I have just taken the internal energy part. Right. Now you can see that this can also be recovered back from a simple balance equation, right? How did we approach here? We started from Reynolds transfer theorem. We did apply a lot of mathematical tricks in order to really come up with the different types of vectorial forms and come up with this differential form. This differential form you can also obtain from what? Say suppose rate of increase of kinetic and internal energy. What is that? The total of that is equal to net. See, I'm basically writing the Reynolds transfer theorem in a more simpler form. I'm taking a differential volume element. Say suppose a Cartesian coordinate system, a rectangular box, and in that rectangular box, I am applying a kind of balance principle, which is the more conventional way of doing the balances. And from there, I'm trying to figure out. So what is the rate of increase of kinetic and internal energy? So that is equal to net rate of kinetic and internal energy addition by convective transport, net rate of heat addition by molecular transport. So this is the convection part, this is the conduction part. Rate of work done on the system by molecular mechanism, that is the stresses, and rate of work done on the system by external forces, gravity. So these are the stresses, these are the gravity, this is the conduction, this is the convection. So I identify there are 4 different origins. You can add as many if you like. So suppose if you are having a nuclear fission, so you have to add really the nuclear perspective, right? Say if you have a Brownian motion, you can really add the perspective of Brownian motion here. But for the time being, in order to simplify the whole thing, what we are doing, we are telling that the increase in the kinetic and internal energy is nothing but something happening due to convection, something happening due to conduction, something happening due to the stresses. Some molecules are moving against each other, and that is generating some sort of heat. And then the other is the this work done. If any of the surface forces are working, there will be heat generated. If any of the volumetric forces are working, then that will be generating heat. So you will see that these 2 components, a part is taken here, a part is taken here. So this part is actually responsible for heat generation. That's why this is coming with the internal energy. Whereas this part is generally responsible for the work done. So that is what is going to the kinetic energy, right? So that's what exactly we are just taking those 2 parts of the, say, suppose some thermodynamic process is ongoing, suppose some work done is happening. In that, what is that part that is coming to the, what is that part that is coming to the internal energy and kinetic energy, right? So here you will see that again, this is at the level of both, that E plus half V square. So what is that? You see that here it is given that del X, del Y, del Z. So suppose if you have a rectangular, if you have a cube, differential cube, right? So and del T is the change of temperature, and what you are doing half rho V square plus rho into U. So this is per unit volume, mass per unit volume. This is mass per unit volume into U cap means it's a specific internal energy, right? Now when you are doing del Y, del Z, Ex at X, right, and X plus delta X, that means through this del Y, del Z plane, how much energy has come in from X to delta X. Similarly, you see that happen to Y. Similarly, that you happen to Z. These are the surface components. And this is again the rho into, this is the total volumetric component that is changing. And then if you add them in a differential volume, differential equation, you exactly end up getting the same equation that you had obtained here. No, from the Reynolds transport theorem. But for the time being, I'm just showing you what is the overall picture of the whole game and all. But for the time being in heat transfer, I just really did not worry about too much about all these different aspects, because this is perhaps by the time of 4th year, once you really are an expert in the transport phenomena processes, it will come up to you in a big way. I just wanted to show you what is the entire game here. But you just need to worry about here. You just really need to worry about here. I just maximize a little bit. So then it will be visible to you. This part is important. What you really need to worry about in your heat transfer is that first, you understand how exactly internal energy is correlated to this transport equation. And then internal energy is converted to enthalpy. Why am I going for enthalpy? Because all my engineering systems are open system. So first I do a balance with internal energy, then I replace the internal energy parameter with the enthalpy. And once I get to the enthalpy, what I do, I say that enthalpy is nothing but enthalpy has a correlation with the temperature, right? We know that H has a very big correlation with the CPDT, right? You have a very generic correlation with H and CP, and that I enforce in this equation to get an expression for the temperature. So rho Cp dt by dt equal to minus of divergence of Q. तो जितना खिचड़ी लास्ट 3-4 क्लास से पक रहा है, just to make you understand that where exactly the Fourier law of heat conduction is originating. So essentially, I am first doing a kind of Reynolds transport theorem, and from Reynolds transport theorem, I am replacing the scalar parameter to be energy. That energy I am defining as two components, internal energy and kinetic energy. Why? Because internal energy is giving me the idea of the heat, whereas kinetic energy is giving me the idea of the net work done. In that, I'm replacing the internal energy with enthalpy. And when I'm replacing the internal energy with enthalpy, in order to really tackle the open systems, the enthalpy has a correlation with the temperature that I am bringing in, right? And from there, I'm able to first say that what, this is the first equation that I'm obtaining. Let me just magnify a little bit for you, because many of you are following it in mobile phone. So essentially, like, rho Cp dt by dt. What is the component here? This is nothing but the change of internal energy that I am talking about, but I have brought in, from what internal energy to enthalpy to the temperature is having what? Is having this divergence of Q. And what Fourier says that, this K is equal to what? This Q is equal to what? Is minus gradient of delta T, minus K into gradient of delta T. Who told him this part? Nobody told him, right? He performed a number of experiments, and from those n number of experiments, he got the evidence, right? That this Q will be proportional to the gradient of T. And then from there, if these are our molecular mechanisms, this Q will be the proportional of gradient of T. And then, he put back into this divergence of Q in order to get the most comprehensive equation of what? This is the most comprehensive equation of the unsteady state. This is a three-dimensional unsteady state heat conduction equation, right? Which will be in our focus. Of course, we will also integrate convection and all these things as we progress. But this is the origin of your most famous equation, which is associated with what? Which is the one, like, we study in our first chapter of heat transfer. That is called what? That is called the conduction, right? You need actually this sort of background first in order to really get going, like, why suddenly I started looking into all these things. So essentially, when I show you a block like this, you should be first thinking about this is a part of a whole system. This is not a kind of independent system. It is not a kind of mathematical problem. It's an engineering problem. Maybe it is situated inside a heat exchanger. Inside there is a liquid flowing. Outside maybe inside there is a hot fluid flowing. Outside there is a cold fluid flowing. Now, there is a heat exchange that is going on, which is setting up a kind of temperature gradient here, right? Now, when you set up a temperature gradient here, you say that there is a heat flux, right? There's a heat flux associated with what? What is heat flux? Heat flux is this Qx. Say, suppose this Q is coming here. This is Q at X. This is Q at X plus delta X, right? And if the area perpendicular to the heat flux is perpendicular to the flow of heat or the transfer of heat is A, right? So you say Qx by A is your heat flux, and that is what is proportional to what? Del T by del X. Now you see very easily. So if K is like this, then what I can write? Then you can straight away see in three dimensions what I can write. Q is equal to what? Q is equal to what? Minus of, say, suppose Q is proportional to what? Minus of what? Gradient of T. Why minus? Because heat will always be flowing towards hotter to colder, so final T is less and initial T is higher, right? So and who said this? Nobody said this. These are all phenomenological correlation. From where is it originating? Say, if I ask you, who told you force is proportional to momentum, rate of change of momentum? Who told you this force is directly proportional to rate of change of momentum? Nobody told this. This is a phenomenological correlation. Actually, this particular correlation doesn't hold good at the subatomic levels. That's the reason why you have developed an entirely new subject called quantum mechanics, right? So you have to really keep in mind that these are not exclusive laws, but these are all phenomenological correlations. Like, say, Newton's, you are learning Newton's law of viscosity, right? Where is it said? What is it said there? That stress is proportional to, like, the strain rate. And from there you get a proportionality constant called viscosity in order to get, like, tau equal to minus mu du by dx. How do you know that? You know that there are fluid which are non-Newtonian. You know that there is a fluid called pseudoplastic, dilatant, and all these things, correct? So these are all phenomenological correlations. People have performed a number of experiments, and from there they have found out that, oh, this group of materials, they behave this way. And I can really found a kind of law which is followed by this in this domain, in this set of parameters. This particular law is applicable, which gives us the Fourier law of heat conduction. What is that? Say suppose if this is a metal, and is suppose, like, if the molecules are not moving, they are stationary in nature, right? There is no convection, there is no movement, there is no movement of materials. Then what happens? These molecules, say suppose if a molecule is receiving some heat, it is going to transmit some heat based on the conductivity of the material, right? And in that sense, you will find in the beginning the temperature is higher, but as you go across the material, you will find the temperature will progressively reduce, right? And this will lead to the establishment of a temperature gradient, which is dt by dx. dt by dx in a one-dimensional coordinate system, but in a three-dimensional coordinate system, it will be the gradient of T. And this gradient of T will be what? So if I really calculate the heat flux will be proportional to this gradient of temperature, right? And you exactly see the same thing we had obtained. Where is that? Same thing we had obtained, that if you really ignore all the convection, all the other terms, if you just only focus on your convection, if you really only focus on your steady state convection term, if in your energy balance, if you really focus on your steady state convection term, sorry, if you really forget about all the velocities, velocity to be zero and all these things, if you really focus about the steady state convection term, steady state conduction term, so you will find that Q is just equal to minus of gradient of T, right? Yes. So you may see. So this is the starting point. This is a first hypothesis, and then tested over a different types of materials. So if I take a kind of one-dimensional infinite box, semi-infinite box, and in that I say that x is the length and dx is the differential length. My slides are visible to all of you, right? Am I correct?
Yes.
Just confirm. Okay, thank you. Yeah. So how do I go about it? How do I recover the same equation from the differential volume element? Now say again, I enforce the same thing. Energy conducted in the left phase. Heat generated within this element. Okay. Change in the internal energy in the entire place, and energy conducted towards right phase. So why am I writing this? So this is what is happening. This is what is, say suppose if I look at this, pink differential element. So if I really want to make a budget of energy inside, so something is coming here and some heat is generated. So this is the gain to this particular point, right? Whereas, once it gains, there will be some change in the internal energy of the system. So you really store a part of it. You know that, when the heat is transferred, always there is a storage, right? So that storage is the change in the internal energy inside the system, and a part is going out. So this is your loss in terms of heat transfer. In terms of, like, total heat is coming in and going out. So a part of the heat is going to come in. So suppose, this material has a very less heat capacity. So you may see that this part will become zero. But however, but in case, if this particular material has a very high heat capacity, then what happens? then it will retain a lot of heat and it will allow less heat to go, right? So energy conducted in the left phase, heat generated within the element, change of internal heat. How can heat generated within the element? There can be a reaction, there can be an exothermic reaction inside the system that can generate heat. There can be a nuclear reaction that can generate heat, right? So what is through the left phase? What is coming? Minus Ka dt by dx, that is coming through the left phase. The same thing is going out, at x plus dx. Same thing is going out from x plus dx. What is the heat generated? What I say that Q dot is my rate of heat generation. I put a kind of generation term here, which is watt per meter cube, right? And then I multiply this area A into dx. So that is the total volume. So if at a particular point, if I have this much amount of per unit volume heat generated, in the total volume, the heat generated is this. Whereas the change in internal energy, that mc delta T, right? mc delta T. So now what I do, I put rho, that means m by volume, and then A dx gives me the volume. So that becomes m, c, and dt, right? Now delta tau is coming what? Because this is all rate equation. This is the rate of heat transfer equation. Correct? Now, so C is the specific heat. So if I just add this, and then if I put the differential elements on, so what I get, del square K del x of K del T del x plus Q dot rho C del T by del tau. Again, the same equation you can now see I have obtained from the Reynolds transport theorem. Just a minute back I had shown you that part. That is the same equation. So this is in one-dimensional space. In a three-dimensional space, how will it looks like? So Q dot will be equal to, if I ignore it's in a steady state, so Q dot will be equal to minus K of Laplacian T del square T, right? So it will look like what? It will look like if I say that it is in steady state, this will become 0. So Q dot will be equal to what? Q dot will look like in a three-dimensional space minus of K into del square T. So I put minus here and I put this as K. Okay. So minus K into del square T. So you can very easily see that just simply by enforcing a kind of shell balance equation for this particular element, we are able to get what? We are able to get the same equation that we have obtained previously. Now this is a much simpler one-dimensional equation, and we'll see how to play around with this mathematics, because first we should be happy with the one-dimensional, then we should be comfortable with the two-dimensional, then only we should be moving to three-dimensional. First we'll be very much comfortable with simple geometries like slab, like say suppose pipes, those who are regular geometry and it's mathematically possible to really tackle. And then we'll go for the complicated geometries like say suppose a microprocessor, like say suppose a kind of a heat engine, right? Like say suppose a kind of boiler, like say suppose a kind of turbine. So, you will see initially it is possible to do all these things analytically. And as you progress, you will see that to really do things, solve these equations numerically, and then come up with the solutions, which is called a very famous subject called the computational fluid dynamics and computational heat transfer, right? So initially the equations will be as simple as this, and you will have analytical solutions, and then later on, what will happen, this will become more a kind of I mean, you cannot solve these equations if you can see if it goes to 3 dimensions. You will have a lot of complications associated with the dimensions, their boundary conditions, non-definiteness of the geometry, and from there you will have the issue in terms of solving the problem, right? Great. Now, so just to give you an example how complicated it can be, so the same thing if I enforce in a 3D. So what happens, I have qx, qy, qz coming through, say suppose x, qx plus delta x, y, qy plus delta y, qz, qz plus delta z. So these are the 3 heat conducted at xyz, and this has gone out at x plus dx, y plus dy, z plus dy. Now this is the heat generation, this is the total internal energy change. If you accumulate all the terms in all the surfaces, right? So you end up getting an equation. So again, you see now this is what? This is your Laplacian, del square T, this we have derived, right? Plus, Q dot by K, okay, is equal to what? Is equal to 1 by alpha. Now you see that we have come up with the definition of alpha, which is called the thermal diffusivity. What is thermal diffusivity? What is alpha? Alpha is K by rho C. This we have already talked about. And alpha is coming from where? This is the change in the internal energy, the heat capacity, and K is coming from here as a denominator. So 1 by alpha is coming for K by rho Cp. This is what K is, how much heat is conducted. How much heat has diffused, how much heat has diffused from this place to this place, from this place to this place, from this place to this place. Because this is a molecular mechanism, this is called the diffusivity. Whereas rho C is what? How much heat is stored. So whatever heat is coming to a system, a part will be stored and a part will be diffused. And the ratio of these two is called the part which is diffused to the part is stored. This ratio is called the thermal diffusivity. Now, somebody asked me the question, sir, what is steady state? Now, this is an unsteady 3D heat conduction equation, correct? Because I am looking at how temperature is changing with respect to time. In that, I can assume that, with respect to time, variation of temperature with respect to time is not there. And this happens with many situations. Say, suppose you have taken a kind of cooking utensil, right? And you are cooking. So initially the cooking utensil will be a little bit cold. But as you start cooking, after some point of time, what will happen? This particular cooking utensil will reach a particular temperature. And beyond that particular point, you will not see that this cooking utensil is getting heated up. Right. That means, whatever heat it is receiving, whatever heat it is storing, and whatever heat it is going out, there is a kind of, steadiness associated with the amount of heat received, amount of heat stored, and amount of heat, dissipated. Now, when those sort of things happens, so you say that, temperature is only varying with respect to space. So if I really consider temperature is a function of X, Y, Z, and T, right? And where if I really allow the temperature to vary only in X, Y, Z, and I don't allow the temperature to vary with respect to time, so that is called steady state situation. Whereas if I really allow the system to vary with time, it's called the unsteady state equation. Okay, so this is the overall part with unsteady, and then we differentiate between steady and unsteady. Now you see that when you have this sort of equation, in terms of differential form, this is the 3D differential form. This is taken again from the previous slide, right? Mu5 you just forget because I'm not considering convection here. So these two parts are coming from that previous equation. Now this you can also write in the form of the cylindrical and spherical coordinates. And the rule is very simple. Right? This is the transformational matrix that you have to do. That say suppose you know that this is del square T by del X square, del square T by del Y square, del square T by del Z square. How do you transform this to a cylindrical coordinate system? What you do, you say that X is equal. So first you define a coordinate system. You just remember this coordinate system. Rest will be straightforward, as straightforward as this. Okay. So suppose you have put forward a Cartesian coordinate system and you want to really convert into a cylindrical coordinate system, right? So what you do, you assume a cylinder around it. The cylinder is having a radius r, and that radius r is the contour of the cylinder that is sitting here, right? The cylinder is something like this that you assume, right? So now if I join r and if I say that it is making an angle with respect to theta, so can you tell me what will be the x with respect to r and theta? This r is the position vector of this particular point, right? Now what is x? What is x? If r is the radius of the cylinder, what is x?
R cos theta.
R cos theta. What is y?
R sin theta.
What is Z?
Z.
Z remains to be Z, right? Z remains to be Z, right? Similarly, if I have placed a sphere here, and this particular point is on the surface of the sphere, and the radius of the sphere is R, right? And this R is making an angle theta with Z. Now, if I project this particular point on the XY plane, there will be another vector, right? Another position vector here, which is making an angle phi with X. If I define that way, then you tell me in this situation, what will be my Z?
R cos theta.
R cos theta. When I project P on this particular plane, this is R dot, right? So what will be my R dot?
R sin theta.
R sin theta, right? So this is my R sin theta. So what will be my X? What will
R
be my
sin theta cos phi.
R sin theta cos phi? And what will be my Y?
R sin theta sin phi.
R sin theta sin phi. So you see that Z is equal to R cos theta, X is equal to R sin theta cos phi, and Y is equal to what? Y is equal to R sin theta sin phi. So now if I have this transformational system, so what I can do, I can define R from these equations. I can define theta, I can define Z, and del X. What will be my del X? Can anybody tell me what will be my del X? How do I calculate my del X? What is the method to calculate del X? Say suppose I am taking a scalar chi and I'm trying to make the transformation with respect to X, right? I want to really make del X. So what should I do? You see that, see del X of chi, X means, my Y and Z is constant. So I'm using a chain rule, right? So essentially I have to get that X, which is in XYZ, chi, which is in XYZ, psi should be in R theta, right? So you can see that del psi by del R, but then, del R by del X, del psi by del R, del theta by del X, del psi by del theta, del Z by del X, del psi by del Z, right? Now, in that process, you may see that, when I really start with this variable and want to transform to this, I just need to use this rule in order to go for the transformation, right? So, can anybody tell me what is del R by del X in a cylindrical coordinate? Del R by del X at constant YZ. You know what is R theta Z, right? R is equal to what? Plus root over of X square plus Y square, right? What is del R by del X?
So X by root.
But then if I convert it to, so what is that?
So X by R. X by R, so cos theta.
Cos theta, right? So you see that del X is cos theta del R. Right? So this is that component, right? Now, if you calculate del theta by del X, you will see this is minus sin theta by R. What is del Z by del X? Can anybody tell me what is del Z by del X?
0.
It should be 0, right? So you may see that this del X, this del Y, and this del Z can be calculated from this rule, right? If a scalar function x chi, which is a function of x, y, z, is to be transformed into psi and r theta z. So this is, and all these are possible. You just need to remember these two geometry, and then you form these transformational rules, and from there you calculate using this rule. You calculate these. This is for the spherical coordinate. This is for the cylindrical coordinate. And if you put back into your equations, you are going to get what? Where is my cylindrical coordinate system? Yes. So you end up getting, just go for this del square t, and that del square t you replace by here. You get, this is the cylindrical coordinate equation, and this is the spherical coordinate equation. Now, a bit complicated. Require a lot of algebra, but it's very easy to conceptualize from where these things are coming. And you can make use of these these transformational things in order to really get them. Anyway, don't worry about your exams and all. There, all these things will be supplied for you. And generally, this sort of exams are taken for open book exam. So, but then I will suggest all of you to really practice once, converting this Cartesian coordinate equation to the cylindrical coordinate equation. And in order to enforce that you practice once, I may ask this you to derive during the quizzes, one of the quizzes. So be very careful that I will really like to see that you have at least done by yourself once. I did not want you to remember, but just the way when I teach, I remember all these things, right? Because I did once, how does that happen? Right. And that will actually keep you on the pace that even if you don't have any material and all, at some point of time in your profession, if you require these things today, it is as simple as that. You don't need any help or book in order to do all these things. Right. So I think, I stop here today because time is up, and we'll continue on Monday, try to finish this heat conduction part. And then, we will have the tutorial on Tuesday. Any question you have up to this point? Any question you have?
Sir, this where are the slides, lecture slides shared actually?
It is there in the drive. That is there in the drive, right?
Yes, sir. Up to whatever slides you gave me, that all are uploaded there.
Yeah, please upload this one also and share with them once again. Okay.
Yes, sir. Fine.
Yeah. So you will get an email. Where are those slides? Okay.
Okay, sir. Yes,
and
sir.
I'm following two books. One is Transport Phenomena, Birds Toward Lightfoot, BSL. Okay, and second is this Holman, JP Holman. So all this you will find in JP Holman. Okay.
Yes, sir.
Line by line, I will be following JP Holman with all the other wisdoms that are coming from different books, but then that will be there in the lecture notes. Okay. Yeah. Any other question you have? If not, then thank you. Let us meet on Monday. Thank you so much. Bye-bye.
Thank you, sir.
Thank you, sir.